So today we will be discussing about the theorem parallelograms between the same parallels and on the same base have equal areas. Alright. So here what I've done here is I've drawn a parallelogram. You can see it here. I've drawn a parallelogram, and the parallelogram is ABCD. This is a parallelogram. Okay, and this is another parallelogram here, DEFC. Alright, so first of all, let us first try to understand what is the meaning of on the same base. So on the same base means that these two parallelograms will have a common side. Now if you compare these two parallelograms, you can see the sides of the first parallelogram. It's AB, BC, CD and DA. And if you look at this other one, it is DE, EF, FC and DC. So can you see a common side between the two parallelograms? So you can see that DC, you see DC is clearly a common side of the two parallelograms because it is a side of the first parallelogram. It is also a side of the second parallelogram. So it is a common side. Alright. So this common side is taken as the same base. So same base here basically means common side. So common side could be, any side. It could have been this, it could be this, it could be this, but in this case, in this particular case, DC is the common side. Alright. So now you can see that this AB has been extended on both sides, and we are getting an L with a line L, which is being an extension of AB. It must be parallel to DC because AB is parallel to DC. You know the reason why, because ABCD is a parallelogram. So obviously AB and DC are parallel. So let me mark them parallel, okay, for your convenience. So let me mark them parallel. So AB is parallel to DC. So because L is an extension of AB, it must also be parallel to DC. Alright. Now what we can see is that the vertices which are opposite to the common side or the base, so this is a common side, and so which are the vertices opposite to the common side? For the first parallelogram, it will be A and B, and for the second parallelogram, it is E and F. So you can see that the vertices opposite to the common side for both the parallelograms, all of them lie on one straight line. So that's very important, okay, that this theorem is only applicable when the parallelograms lie between the same parallels. Okay, so what is the meaning of same parallel? That is very, very important. Between the same parallels. So what is the meaning of this? So between the same parallel means that the vertices that are opposite to the common side, that means these vertices E, F and B and A, all of them must lie on the same line, and that line must be parallel to the common side. So that is what we mean by between the same parallels. Okay. So now you can see that these two parallelograms are lying between the same parallels and on the same base. So what are we supposed to be doing now? To prove that the area of ABCD is equal to the area of EFCD. Okay, now let us study the area of ABCD. You can see that this diagram ABCD is made up of two parts. You can see one is this triangle AED and one is this part EBCD. Alright, and if you look at the parallelogram EFCD, you see a similar thing. This EBCD plus CBF, these two areas make up the parallelogram EFCD. So we can see that this EBCD is an area which is common to both the parallelograms. So what I am going to do now is I will just shade this area, okay, the common area. So this is a common area. Let me shade it. this is a common area. Yes, I'm just shading this common area. Better if I shade it this way. Okay, this is it. So this is the area which is, common to both the parallelograms. Okay. So now what about the areas which are not common? So one of them is this and the other is this. Okay, so let us study these areas. Now these two areas, we can see they are triangles here, and we can see that AD is parallel to BC. You see, AD, this one, is parallel to BC, right? And this is a transversal. Okay, so you know that you can see what kind of a formation is. This is DA, this parallel line, and this. Okay, so this and this form an F, and therefore this angle and this angle are corresponding angles, and you know that corresponding angles formed by parallel lines are always equal. And you know why are these two parallel? Because ABCD is given to be a parallelogram, so obviously AD and BC are parallel. So these two are corresponding angles formed by parallel lines. So let me mark them equal. So this is equal to this, that is x and x. And similarly, this angle and this angle are also corresponding angles formed by the parallel lines CF and DE. And you know why they are parallel? Because EFCD is a parallelogram. Alright. So therefore these are also corresponding angles, and they must be equal since they are formed by parallel lines. So in these two triangles we can see that we were getting two angles equal. Let me write it down. Angle ADC is equal to angle FBC, because they are corresponding angles formed by parallel lines. Corresponding angles formed by parallel lines. Okay, parallel lines. So angle ADC is equal to angle AED. I am wrong there. This is angle DAE, right? DAE is equal to FBC, because they are corresponding angles formed by parallel lines, and angle AED is equal to angle BFC, also because they are corresponding angles formed by parallel lines. And which parallel lines? The parallel lines ED and CF. Okay, and also AD is equal to BC. And why are they equal? Because they are opposite sides of the parallelogram ABCD, right? Of the parallelogram ABCD. So that means that these two triangles, triangle DAE is congruent to triangle CBF, and you know that congruent triangles are exactly the same. So if they are exactly the same, they must have the same area too. So we write down area of triangle DAE is equal to area of triangle CBF, right? Okay. So now so what have we proved? We have proved that these two triangles are congruent and so they have got the same area. Alright, now what we can do here is, okay, let me just do this and erase this. So what have we proved just now? We proved that area of triangle ADE is equal to area of triangle BCF. And why? Because the two triangles are congruent. Alright, but was this the thing that we wanted to prove? Well, no, because we wanted to prove that the parallelograms have equal areas. So how do I get the area of the parallelogram from this triangle? So it's the area of triangle ADE, okay, when added with area of triangle ADE when added with EDCB, you see. So this area added to ADE will give you the parallelogram ABCD. So therefore, what do I do? So I will just add area of triangle ADE. I will add it to it. In fact, I will add to it area of EBCD. Alright, and if I want to keep the left and right equal, then to the other side also I have to add the same thing. So that is area EBCD. Okay. Now what is area of triangle ADE? So let us look at it again. So this is area of triangle ADE, and to it I have added EBCD. So this area and this shaded area together, doesn't it give me area of parallelogram ABCD? So I can write this as area of parallelogram ABCD. Okay, and the other side you can see again the same thing. This area of FBC, I've added EBCD with it. So this shaded area and this small little triangle here together gives us EFCD. So therefore I will write here EFCD, area of EFCD, which is a parallelogram, right? So I am getting area of the parallelograms are equal. Okay, so that is how we prove that parallelograms between the same parallels and on the same base have equal areas.